Yes, am I audible? Austin, Tarif, Rabia, Shahid, Chavez.
Yes, ma'am.
All right. See, we have to start with the fourth lesson, that is magnetic effects of current. So this timing, we are just having it for today only, the class. Otherwise, your regular class will be from 6:30 only. Like tomorrow, you'll be having your class from 6:30 only. See, now three things we have discussed. Two things we have discussed. Initially, we had seen electrostatics.
Ma'am,
Yes.
from 3:30 to when this class will end?
Same timings, 1.5 hours.
Okay.
So, see, we had seen one thing, that was electrostatics. In electrostatics, what did we see? Charges were at rest. There were certain properties that emerged due to the presence of a charge. Like we had seen the concept of electric force, we had seen the concept of electric field, then we had seen the concept of electric potential. All these we had seen. Now, after this electrostatics portion, including capacitance, then second thing which we saw was when the charges began their motion, right? Initially, we were not considering any charge. Now, when the charges have started moving, we then started considering the velocities also. Drift velocity, we had seen acceleration was also involved, and the charges moved. So these were the two things which we have already studied. Now see, if the charges are moving, there was a question that arises that will they produce magnetic field or not? Magnetic fields concept was done through Oersted experiment and lots of experiment that you don't need to now. You don't need to do. It's there in NCERT, in your reference books. It's there, but it's not included in now in your CBSE syllabus. So magnetic field is now easier to understand because you all have already studied about electric field. So it is similar to electric field only. It's the space around a charge where you can feel magnetic properties. When I say magnetic properties means attraction or repulsion you can see. See, for example, if I say there is a bar magnet that is present. Suppose this is a magnet that is present. One end of it has north, another polarity has south end. So around this magnet, no, you will see certain lines of force which are existing here. Certain lines of force which are existing. Like, so what happens if you bring another magnet? If you bring another magnet or any other object, then if it also has magnetic properties depending upon its pole, you will either feel attraction or repulsion. So this space around the magnet where you are able to observe its attractive forces or repulsive forces, that space, that confined space is known as magnetic field. Similar to electric field also we had seen it was the space around the charge. This is just the difference. Otherwise, whatever you have studied about electric field, the basics will remain same for magnetic field. We'll have everything here also. We'll have dipole moment also here, similarly to what you have studied to in electric field. So the way around a charge, around a single charge, a field exists, right? So here also in magnetic field around the magnet, it can be a bar magnet, it can be a horseshoe magnet, it can be a magnet of any type. So when the magnet is present around that, certain forces, lines of force exist in that space only, in that region only, you are able to feel the forces of attraction or repulsion. So that is known as magnetic field. And how do we represent? We represent electric field by capital E. Force, we have F, right? We have certain symbols. For potential, we use V. For voltage, this is represented by B, and it's a vector quantity. So, and the most important quantity where you will see directions are getting involved. Lots and lots of questions will be asking you separately the direction. Just the direction will be asked you separately. SI unit is Tesla. And CGS unit is Gauss. That is capital G. Yes, we have just started the chapter, Madhya.
Ma'am,
Yes, Chavez.
Here, magnetic field is represented by B.
B.
Okay.
Magnetic field is represented by B. Why am I saying? Because you will find M also written, but M will be representing you the magnetic dipole, or a capital M will be representing to you something else. So for magnetic field, we have B. B symbol is there for magnetic field. Now, this is a lesson where you can need this conversion. See, I have told you in the first lesson that SI unit of charge is coulomb, CGS unit is electrostat coulomb, ESU. But nowhere in any numerical you needed that, right? Because we had the common unit as the SI unit for the charge. But in magnetic field, you will notice that sometimes the questions are also given in Gauss. 3 Gauss of magnetic field exists like this. So there you need to convert it. So 1 Gauss is equal to 10 to the power minus 4 Tesla. Or you can remember one thing, 1 Tesla is equal to 10 to the power 4 Gauss. This is the conversion, and this is an important conversion. Why? Because out of all the conversions which we have, this will be using. This is going to be used. Sources of magnetic field. Regarding the sources, see, basically you have all the basic sources only we'll discuss, because magnetic field can be generated by many things. Do you remember the intrinsic electronic spin? You must have done in your chemistry structure. I think in structure of atoms you have, you had, when you had to write the electronic configuration from there, N, P, and then M, S. From there you have obtained the spin as plus half, minus half. Did you all do this in class 11th? I think in chemistry you must have done, no?
Yes, atomic structure.
Yes, in structure of atom, right? So there you must have done everything we calculate, I think there, M and S, magnetic spin, moment and all. So this exactly, this plus half and minus half which we write, this is actually the intrinsic spin of electrons. From there also magnetic field is generated. That's why when electron moves, we say
Ma'am, this is the opposite spin.
Yes, Chavez?
This is the opposite spin.
This is the opposite spin. Yes, the opposite spin that occurs. Plus half and minus half, we take it. No. So out of which, see, in detail, if you see, you have to then go according to the spin axis of rotation of the electron and everything. But just you can remember that you already know that electrons spin. So that spin or that movement of electrons also create up your magnetic field. Second most important, which is very, very important for you in your class 12, is current carrying wire. See, till chapter number 3, we have studied what is meant by current carrying wire, how to calculate the current in a wire. So now after this, in chapter 4, in this lesson, we will be using this value of current which we have found. If the current is present, how will it be generating a magnetic field? And the first topic is only your Biot-Savart's law, which we'll do today. That is current carrying wire. Then you have proper magnets are present. Bar magnet is there. Different types of magnets are there. Horseshoe magnets. These are very common magnets. Bar magnet, horseshoe magnet. Horseshoe, see, horseshoe magnet you must have seen. See, bar magnet is like this. When North Pole is there, South Pole is marked. You must have seen this type of magnet. This is a horseshoe magnet. In your, I think, practical labs, in physics labs, this magnet is present. Usually in the labs it is there. Then we have proper solenoids. These devices are there. This also is a part of this lesson only, after we discuss Ampere's circuit law. There are many things else also from this. See, if you look at it, if you look at those, the magnetic spin. See, suppose if you take the magnetic spin of electrons. So after the magnetic spins of electron, even your iron core which are present, the iron cores which are present, Fe3O2 or Fe2O3, all these which are present. So they are also iron bars which are present in under the earth, under the crust of the minerals which are present, magnetite ore, hematite ore, all these are present. What is their exact formula? I do not remember. Fe3O2, Fe2O3, these two exist, right? So they are also the sources of magnetic field. Apart from this, then we have proper Biot-Savart's law only. You have one oyster experiment also, but don't do that. This is a tough experiment and you don't need to go into the details of it. Just quickly note it down so that we can start with Biot-Savart's law. See, next topic is Biot-Savart's law. Biot-Savart's law is analogous to Coulomb's law. The way Coulomb's law helps you find out force, here Biot-Savart's law helps you find out magnetic field, magnitude of magnetic field using certain data which are given. Suppose if you have a wire, right? You have a wire. I have chosen a point, let's say here I have chosen a point P. So separation of the wire from the point, let's say this is some position vector R. This is R. This is the separation of point P from the wire. And I want to find out at this particular point P, what is the magnetic field which is present. Fine. Suppose the current is moving in upwards direction, which is I. Now I have taken a very small section. Let's say this is DL. DL, I call this as current element. Now what is meant by current element? Current element is just a small segment of the wire. So whatever is the direction of current in the wire, that will be exactly the direction of current in this segment also. Because sometimes we cannot take the entire wire for the calculation. That's why we take a portion of it. So that small segment of wire of length DL, this is known as current element. So it has the same direction as that of the current. One more quantity that will be used over here is the angle that is being made between this DL, that is current element, and the position vector, which is theta. Now, what does the law say? Biot-Savart's law basically says four things. That your magnetic field is proportional to four things. Firstly, you have the first quantity as the current which is flowing in the wire. So the first quantity is current. Then it is also directly proportional to this current element, DL. Current element. Secondly, current element. Thirdly, this is directly proportional. Remember, we had seen the angle between the DL. Yes?
What is current element?
Current element is just a segment of wire, a small segment of wire which I've taken. Suppose if this is a wire, if I take this small part, that is known as current element. Because every time it is not easier to define the entire length of wire. So we take DL. Depending upon your wire, you can change the values of DL. If we will see in the derivation also, if you have a circle, so entire length of a circle will be 2 pi r. So like this, you can keep on changing the values of DL, and that is not fixed for every wire because every wire is different. The length of every wire is different. If it is shaped into different shapes, then that becomes different. That's why we just take it as general, that is DL, current element. Clear, Shaviz?
Yes, sir.
One more thing, we had seen the angle between the current element and the position vector. So this is proportional to the angle with the sine value, sine theta. It is directly proportional to sine theta. So three things it is directly proportional. One thing it is inversely proportional, which is 1 by r square. Remember in Coulomb's law also you must have seen the value of the Coulomb's law of force. F is equal to K Q1 Q2 divided by r square. So here also you have r square, that is inverse square rule only. See, suppose if I combine all of this, what is magnetic field proportional to? It is proportional to, this is directly proportional to current, DL, sine theta, and inversely proportional to r square. So what is the value of the entire magnetic field, which is equal to a constant we will put. Now what is the value of constant which comes here? So value of constant is mu naught divided by 4 pi. Yes, say.
What is the sine theta?
What is the
Sine theta.
sine?
Sine theta.
Sine theta, this you are asking.
Yes, ma'am.
See, sine theta angle between the D and DL, that is the current element we take. So current element is DL and the position vector is R. So suppose this is the wire. I have taken a point here. So there will be a separation from here. this angle that is being subtended, this is what we take it as theta. Angle between the current element and the position vector. Position vector is separation from the point. Because you have taken a wire, you can find out current here also, you can find out current here, magnetic field here also, magnetic field here also. If the separation is there, that separation and the current element means the wire, that angle we take it as theta. The constant that we put here is mu naught by 4 pi. So rest of the things that become I dl sine theta divided by r square. This is your main Biot-Savart's law formula. So if someone asks you what is the Biot-Savart's law, then Biot-Savart's law is basically mu naught by 4 pi. Fine. And what is the law? The law says that, Biot-Savart's law says that magnitude of magnetic field is directly proportional to current flowing in the wire, current element, sine of the angle between current element and position vector, and inversely proportional to the position vector. This is your law also, and if you combine it mathematically, that becomes your formula also. Now mu naught is different. In your electrostatics, we had seen this quantity K, which was 1 over 4 pi epsilon naught. So its value was also 9 into 10 to the power 9. This epsilon naught was present when you have reference to electric field. But now we are talking about magnetic field. So in magnetic field, you have mu naught as the constant, which is known as the permeability of the medium. So absolute permeability of free space, we call it absolute permeability. Why? Because this is not relative. We will be calculating relative also. The way we see epsilon r for relative permittivity. This is permeability. This is basically how different media affect your magnetic field. Suppose if I take a bar magnet and I keep it in air, I have got a specific value of magnetic field. Now, if I take that same bar magnet and I dip it into water, will the effect of magnetic field will be exactly the same? No. Magnetic field will change. Now, how much it is changing?
Your
Whether
voice
it
is
is
lagging.
yes. Chavez, you're asking something? So that is known as permittivity. So how does your value of magnetic fields changes with reference to the medium, with respect to different media that is obtained? That is what is known as your permeability. My voice is lagging. Others, please let me know if my voice is fine. Now it's fine, no?
Ma'am, your voice is not lagging.
Okay. Please let me know. Okay, awesome. So yes, this is what is meant by permeability. If I take a bar magnet, I have got a specific value of magnetic field. If I dip into oil, value of magnetic field changes. If I dip it into water, the value of magnetic field change. So these different values of magnetic field, how much they are changing, that quantity, that governing quantity is known as your permeability. Different medium, this is effect of medium on magnetic field. If I talk about this quantity, this is basically effect of medium on magnetic field. Secondly, the value of mu naught. See, this entire constant's value is 10 to the power minus 7. So if I want to write out just the value of mu naught, that becomes 4 pi multiplied to 10 to the power minus 7 Tesla meter per ampere. Or you can say mu naught by 4 pi is 10 to the power minus 7. The way 1 over 4 pi epsilon naught was 9 into 10 to the power 9. Similarly, mu naught by 4 pi is 10 to the power minus 7 with the units Tesla meter per ampere. Just remember, no, this thing. Remember it in this way. See, when you have mu naught, this is for free space. But when I say mu r, any other medium, that becomes relative. Suppose here also epsilon naught was for free space. If I talk about epsilon, that is for any other medium, that is different. Or if I want to find the relative of it, relatively it will be epsilon r. This is relative permittivity, means with reference to or with respect to a different medium, right? That is what is meant by permittivity. Suppose if you have permeability, a different medium is present. Now how your Biot-Savart's law will change? Just the way you have been doing. What do? We multiply epsilon r to epsilon naught to get a new value for your medium. Epsilon naught r epsilon for any medium will be epsilon r into epsilon naught. So in your formula, in your questions, you just substitute epsilon r. You multiply epsilon r. Here also what you will do, you will multiply mu naught. So your magnetic fields formula, this will be mu, it was mu naught by 4 pi I dl sine theta by r square. This was it, what we had discussed. If you are having it for a medium other than air, any other medium other than air, that becomes mu r. This medium becomes mu r. So mu naught mu r ideal sine theta. This is the formula. So nothing new. You just have to multiply the relative permeability with it, the way you have been multiplying the relative permittivity in electrostatics. It is very much similar to it. And you know, mu r's value, when we talk about the relative permeability, you have the knowledge about it in your lesson 5, the next lesson. It is a very short lesson. It is a theoretical lesson, completely theory based lesson with respect to your values of magnetic field. So suppose for ferromagnetic material is a type of material. We have diamagnetic, we have ferrimagnetic also, we have paramagnetic materials. For different types of materials, you have the different values of permeability. So like for ferromagnetic substance, it is almost very much greater than 1. For iron, almost equal to 1000. For diamagnetic, little less than 1, 0.78, something like this. So different values you are having. And one more thing, class, if you are you need to write it in vector form. Just remember dB, magnetic field. This is mu naught I. It is actually the cross between dl and dr, where you can further write dlr sine theta 4 pi r cube. This r will cancel this, so we'll get everything back, and dl r sine theta will be there if you open the cross product. This is how you write it in vector. Coming to the direction of magnetic field, direction is so elaborate that note down all these things first. We'll discuss the direction separately. All right, note it down. Yes, completed. Written, all of you? Yes, no.
Yes, ma'am.
Okay. See, please pay attention to direction class because direction will be used throughout and we have to discuss it once only. This you can note it down later. First, listen to the method. See, there are two methods which we'll be discussing. Suppose this is the direction of current. So first method says that hold the wire in your, yes, this is right hand thumb rule. So you have to use your right hand only. All right. So right hand thumb rule basically says that take your right hand. Suppose this is my right hand. Now hold the wire in a direction that thumb points in the direction of current. So you can look at the screen, look at my hand also. This is my right hand. Now current is upwards. So I have to point thumb also in the direction of current. Fine. Look here. This is the thumb. The current is suppose here. Current is moving upwards. So I will also keep my thumb like this. See, I will keep my thumb like this. Now the curvatures of the fingers, they will tell me the direction of magnetic field. Suppose, take this point A. Now look here, class. This is suppose the direction of current upward. This is the question that is given. And point A is situated here. Now, if I place the thumb like this, at the point A is here towards the left of it. So towards the left, where are my fingers going? Fingers are going out of the screen. They are pointing towards me. The curvature of fingers, the curling of fingers, the fingers are pointing towards me. That is out of your page, out of the screen. So that is outwards. Suppose take here a point B. Current is moving upwards.
Now, can you just explain once again?
I am repeating. See, suppose current is moving upwards. The point B is located on the right hand side of it. So I'll keep my thumb in the direction of the current. I have kept the, see, this is the direction, I have kept the, my thumb in the direction of current. Now at the particular point B, I'm curling my fingers. Look here. At this particular point, what are you seeing? The fingers are pointing towards the screen. My fingers are going towards the screen. That is towards the, into the page. So this is into the page for A point. This is out of the page. I'll discuss this. This is inwards.
So got it. Now.
Yes, Chavez?
Got.
Outwards, you're saying?
No, I'm like understood.
See, let me discuss this. See here. See, this is the current's direction, let's say. Okay, Chavez. Fine. Now, point A. Current is upward. See, this is the direction of current. Current is upward. Point A is located here. So point A is out of the sheet. So this becomes outwards. Suppose this point B, current is moving like this. If I take this again, point B is located on the right side. So on the right side, what is happening? On the right side, the fingers are curling inwards. You have to check where the curvatures of fingers are curling. Where is the curling occurring? Outwards or inwards? Curling is occurring inwards. So this becomes inwards. Now, all of you in the chat column, answer me for this point A. Whether it would be inwards according to you, outwards according to you, all of you. In the chat column, everyone should answer. Austin, Chavez, Rabia, Tarif, Rabah, Madiha, Humam. Shahid. Okay, Austin has answered. Rabia has also answered. Humam has answered. 3 students have answered. Rest of the students. Rabah has also answered. Good. Shavez, your answer. Tarif, your answer. Shavez also good. Tarif has also answered. Very good. I think 2 students haven't answered. Madiha, your answer. See, Madiha, you have to tell me direction of magnetic field at this point A due to this current element, this current wire, carrying current I in the downwards direction. Rabia, you have sent 2 messages. Earlier you were saying inwards, now you're saying outwards. See, inwards should be it. So now current, earlier the current was moving upwards. Now the current is moving downwards. If current is moving downwards, see, if the current is moving downwards, thumb will be in the downwards direction. Now look at the particular point A, where the curvature of finger is going. Fingers are going inwards. Fingers are pointing into the screen, that is towards the screen. So all of you are right. This should be inwards. And look at point B. Current is downwards. Point B is located here. So fingers are pointing outwards, away from the screen. They are pointing towards me. So this becomes outwards. Yes, Rabia. Earlier your answer was right. After that, you have changed your answer and given the wrong answer. That would be for the B point. Method 2. Write down this method first. Then I'll discuss method 2 with all of you. I prefer method 2, but whichever method is suitable according to you, you can use that. Note it down. See, in method 2, basically, you have to place your fingers now along the direction of current. See, look at this. This is a point. Now, this is the direction of current now, pointing towards the right. So you have to keep your palm in the direction of current. This is the first step. So it can be like this. I can keep it like this. I can keep it like this. I can keep it like this. Using your right hand only. See, again, I'm telling, use your right hand. Otherwise, your answer will exactly be the opposite what is the actual answer. Now you have to curl your fingers towards the point. Suppose I am calculating it for a point. I will curl it towards a point. Where is the thumb pointing? Thumb is pointing outwards. It means here we have the magnetic field outwards. Look at this point, B point. This is the direction of current. This is how I'll keep my hand. Now see, I have to curl my hand towards B point, which is located downwards. So I cannot curl it like this. So it means I have to curl it like this. Now this is point B. I'll curl
Can you
it.
repeat?
Thumb is pointing inwards. I'll repeat. See, look at point A. Current is moving towards the right hand side. You have to keep your hand along the direction of current. See. Look here. This is the magnetic, this is the direction of current, right? Current is pointing towards the right hand side. Now you have to, your point B, point A. Firstly, I'm telling about point A. So your point A is located upwards. This is your point A. So this is the direction of current. You have to keep your hand in such a way that fingertips point towards the direction of current. So this is the direction of current. Now I have to curl my fingers towards the point of calculation. Point A is located here. So I'll curl my fingers along direction of current. Where is the thumb pointing? Thumb is pointing outwards. So direction of current is outwards. If the direction, if the point that I have taken is point B. So look here, this is the direction of current. Now point B is located downwards. This is point B. So how can I curl it now? This is not possible. Can I curl it now? It's not possible. If I keep it like this, can I now curl it? See. So where is the thumb pointing? Thumb is pointing inwards. So it means the direction of current will be inwards. So this will be inwards. Now all of you tell me for point A. This example 2, point A, inwards or outwards according to you. This is the direction of current towards the left. Point A I am asking. All of you in the chat column should reply. Okay, yes, correct, Madhya. Austin, correct. Yes, Rabia, Tarif, Chavez, Rabias for point A. Okay. Chavez, your answer. Tarif, right. Shahid is also correct. Chavez, Humam. Madiha has answered. Madiha has answered. Firstly, Madiha has answered. Rabba and Rabia. Opposite answers you're giving. Look, point, this is the direction of current towards the left hand side. Point A is located here. Keep your direction along the direction of current. This is the direction of current. Your fingertips should point towards the direction of current. Curl towards point A. Finger is going into this page. So that is inwards. A inwards. Yes, right. Rabia and Rabba. Clear?
Ma'am, can you explain again?
It's fine, Rabba.
Ma'am, can you explain?
See, direction of, you have to keep your hand in the direction of current. Where is the direction of current? Right or left? Rabba. Current is pointing towards the left.
Yes, ma'am. It's pointing towards.
Yes, current is going towards the left. So if I keep my hand like this, current will be pointing towards the right. So I have to keep my hand like this, right? I can keep it like this, like this, like this, like this. Now, where is the point B? Point B is located here downwards. If I keep my hand like this, I'll not be able to curl it. If I keep my hand like this, for let's talk about A point first. A point. If I keep my hand like this, I won't be able to curl it. If I keep my hand like this, I won't be able to curl it. If I keep my hand like this, point A, now I'm able to curl it. So what is the law? Law says that keep your fingers along the direction of current. I kept my fingers along the direction of current. Keeping your fingers along the direction of current means that you have your nails pointing towards it. So I have kept it like this. Now point A is located upwards, so I curled it. Thumb gave the direction inside. Now clear above?
Yes, ma'am.
If it's not clear, I can repeat once more. See, look at point B. Point B is located downwards. Current is pointing towards the left side. I can keep my hand like this. If point B is downwards, fingers are not getting curled. If I keep the point like this, see, now look, fingers got curled, finger is pointing, thumb is pointing outwards. So if thumb is pointing outwards, then for point B, the direction of current will be outwards. This is how you note it. Note it down. If you are still having any confusion, please ask me and get it clarified. See, this is just a revision of cross product if you have forgot the signs, because signs will be used in your cross products because you have the in vector form also, dl cross r vhc. But if you remember I cap cross j cap, the best method to remember cross product sign is draw I cap, j cap, k cap, move clockwise. Whatever third quantity is left, that will be positive. If you are moving anti-clockwise, third quantity left will be negative. Suppose I cross j, k cap is left and you're moving clockwise, so plus k cap. If you're going from k to j, that is k cap cross j cap, which is left, I cap. You're going anti-clockwise, so minus I cap, like this. You can note it, all those who have forgotten, but firstly, let us practice a question. See, this is a question, I think, from your NCRT only. Calculate magnetic field at the point P. This is your wire on x-axis, present on x-axis, with current 10 amperes. DL, the small segment of this wire which we take, this is the current element. This is given as 0.001 meters. The position vector, separation of the point of calculation towards this axis, this is 10 meters. Fine. So net magnetic field will be what? Angle, we take angle between the position vector and the current element. That is, this angle is given as 90 degree. So the formula for Biot-Savart's law is B is equal to mu naught I dl sine theta divided by 4 pi r square. So sine theta, this term, this will become 1. So magnetic field will become mu naught is 4 pi into 10 to the power minus 7. Current is 10. DL, this is given as 0.001 into sine theta. Sine theta is 90 degree. No need to even write it. This is 4 pi. R is position vector is 10. This gets cancelled. 10 gets cancelled. So this becomes 10 to the power minus 11. But this is just the magnitude. We have studied how to find out the direction. Now look, current is along the positive x-axis. Fine. Point P is on y-axis. Curl the fingers along y-axis. Thumb is pointing outwards. That is towards positive z-axis, k cap Tesla. This is how we have to write up the final answer. Note down the cross product part quickly, all those who need to write, and then this question. Class, just one last thing, then I'll leave you all. If you have current, because one question is there in your NCRT also, and you can encounter this question. If current is dq over dt, that is rate of change, a rate of charge, that is current which you have studied. dB, see, if I write, instead of current's value, if I write this, mu naught by 4 pi, instead of I, if I write dq over dt, what is left? Mu naught by 4 pi I dl sine theta divided by r square. Class, can you notice this quantity? dl over dt. Can anyone tell me what is dl over dt? dl is length, distance, over time,
Velocity.
velocity. Very good, Shavis. Yes, Madhya, very nice. It is velocity. Velocity, it will be dl over. So velocity will be dl over dt. So in case if you have charge and velocity given, you do not use any other formula. Directly use this formula, which is dB is equal to mu naught by 4 pi. This becomes dq v sine theta divided by r square. So what is the cross product that you can use? Multiply and divided by r, or directly use this as mu naught by 4 pi dq v cross r by r cube. This is in vector form. This is in vector form, and this is the normal formula which you can use just in case if velocity and charges are given. Otherwise, use your general formula. Application, we'll do it in the next class. Note down this from here. Just text me done once you have written. All right, now applications, we'll do it in the next class. That is tomorrow at your regular timing only. Yes, I'll scroll it. Rabba. Rest of you, all those who have completed, you can leave. Okay, thank you so much. From here, Rabba,
From according to Savart's law from down.
this one.
This one. Ma'am, done. Down.
This also you have to write?
Yes, ma'am. Just last part.
Okay.
Ma'am, can you show a little down?
Written this part.
Yes, ma'am, I took the screenshot. I will write it now.
And this?
Yes, ma'am, I've read this.
Any other part you want me to scroll?
Ma'am, can you show more down? Like, if I miss anything.
Which one, rubber?
Down only, ma'am. This one down. Like after this, we after this we started direction of magnetic field. Yes, ma'am.
Done?
Yes, ma'am.
I think from direction you have written already, no?
Yes, ma'am. From direction I will. This one is. Thank you, ma'am.
Okay, okay. Thank you.